This is section 16.6, which is about polyprotic acids, and the main thing with polyprotic acids is that they have multiple protons that can be released into the solution. If you think in terms of, for example, hydrochloric acid has the ability to give you only one proton into the solution. But if you look at an acid such as sulfuric acid, which is H2SO4, then you have two protons that can be released into the solution. Okay, so that is the thing with polyprotic acids. More than one proton that can be released into the solution. Classical examples of these polyprotic acids are represented by sulfuric acid and phosphoric acid. And you name these acids in terms of how many protons you have that you can release in the solution. For example, if you have 2, then that's a diprotic acid. And if you have 3, that's a triprotic acid. Those are the more common types of acids that you have. Now, polyprotic acids, they ionize in steps. So if they are releasing those protons into the solution, they will not release all of them at the same time. They do it in a stepwise fashion. So one of the things that we were saying about sulfuric acid is that it's a strong acid, and as such, it will completely dissociate in water. Now, before we got to the point of polyprotic acids, you might be thinking that sulfuric acid will do something like this in solution. Okay? That will represent the complete ionization of sulfuric acid in solution, but that actually doesn't happen in solution. So this reaction does not happen. The sulfuric acid has the ability to release all the protons in the solution, but it will do it in a step-by-step fashion. So if we take as an example phosphoric acid, then with 3 protons, then you will be able to write 3 different acid equilibria for phosphoric acid. In the first step, you will be releasing only 1 proton, okay? And then you will have an ionization constant for that particular step. In this case, you have the acid, the phosphoric acid, H3PO4, and then you will have the conjugate base, which is H2PO4 with 1 minus charge, okay? Now, this is the first step. So you release 1 proton into the solution. Who's releasing the second proton? Well, now, the conjugate base that you have in the previous step becomes the acid in the second step. And that one will release another proton, which is here. And then you have the acid, and now you have the second conjugate base. All right? And for the last step, this second conjugate base now becomes, once again, an acid, up to the point that you obtain the last conjugate base and your third proton. Now, one thing that you will notice here is that Ka1 is larger than Ka2, and Ka2 is larger than Ka3. This is something that you're going to observe in every single polyprotic acid. The ionization constants in each subsequent step is going to get smaller and smaller and smaller. Okay, partially because you are removing a proton for an already negatively charged particle, but also because you have to think in terms of Le Chatelier's principle. And what does that mean? For this, let's look at the second step, right? If we look at the second step, right? Well, you have already released some protons to the solution. And those protons to the solution now become part of your reaction here. And because of those protons that are already in the solution coming from the first step, well, this acid-base equilibria is being pushed. Let's use a different color here. It's being pushed to the left. Okay, so that second step is not so able to release protons to the solution because the protons already coming from the first step are pushing the equilibrium to the left. So it's not favorable for the second step. Okay, so same thing happens on the last step. Okay, those are less and less favorable because of the concentration of protons that are already present in the solution. All right. So some acids that you can be working with ascorbic acid. This is a diprotic acid. Uh, depending on the number of constants that you see here, this is diprotic, this is diprotic. And then phosphoric acid, we have already seen that this is a triprotic acid. Same thing with citric acid. Okay. Once again, whenever you are writing acid equilibria, you can simplify your life by just using this type of equilibrium. So HA goes to H plus A minus. If it's a diprotic acid, then you can use H2A goes to H plus HA minus, and then HA minus goes to H plus A2 minus. Okay, so you can, doesn't matter what acid you're working with, you can always simplify your chemical equation in terms of A, the anion of that acid. Okay? Now, when you're calculating equilibrium concentrations for a polyprotic acid, well, you will use as many ice tables as steps you have in that acid, as many protons you have in that acid. So you have 3 steps, you are looking at 3 ice tables. And the thing that you have to be careful with is that those initial values that you're going to use on the ice tables, particularly on the subsequent steps, the initial values will be whatever you release on the first step. And if it's for the third step, well, whatever you release on the second step is going to become the initial values for your last ice table. So you have to be careful with that. Okay? And the thing that you have to remember is, as I mentioned earlier, is that those steps will be releasing protons in a solution that already contains protons. So you have to be pretty careful with that. So let's work on this example. So we have that for hydrosulfuric acid, we want to know what is the pH, all right, and what is the concentration of the sulfide ion. So what is the first thing that we have to do here? Well, it's hydrosulfuric acid, and hydrosulfuric acid is H2S. All right, and for this, that's a diprotic acid, so we have H plus HS minus, and then we have HS minus goes to H plus sulfide. And I want you to notice you are calculating pH, so one of the things that you have to determine here is what is the concentration of H3O plus or H plus, and the concentration of sulfide. The concentration of sulfide, well, that's this concentration that you are calculating. So you need to use both steps, right? So if we rewrite our first step, we have that HS goes to H plus HS minus, and in this case we are starting with an initial concentration of 0.1, and you have 0 and 0, or you assume that is 0 for the H plus, right? The good thing about acid-base equilibria is that the stoichiometry is always 1-to-1, so the change for the acid is going to be negative, so we call that minus X. It's going to be plus X here, it's going to be plus X here, right? So for the hydrosulfuric acid, then the concentration, the final concentration is going to be minus 0.1 minus X. Here's going to be X, and here X, all right? So if we put all of this together, then the first ionization constant for the acid is going to be H plus HS minus divided by the concentration of H2S. And this is equal for hydrosulfuric acid, this is equal to 8.9 10 to the negative 8. Now I compare 0.1 versus 8.9 10 to the negative 8, and that constant is really small compared to the initial concentration. So basically, when we come here and write Ka1 equals to x times x divided by 0.1 minus x, we can perfectly assume that this x is small so that we can simplify our life, and this becomes Ka1 equals to x squared divided by 0.1. Therefore, x is equal to the square root of 0.1 times 8.9 10 to the negative 8. And this should be equal, just give me a second here to double check. This is 9.43, 10 to the negative 5. Okay, so that x, your concentration of H3O plus is equal 943, 10 to the negative 5, and the concentration of HS2 minus is also equal to 943, 10 to the negative 5. Okay? So if we move into the second step, because we are not done yet, so we have to continue working on our ice table. So the ice table for the second step, if we rewrite our equation, goes like this: H plus H2 minus. So our ice table now is going to look something like this, and this is where you have to be careful if you're working with polyprotic acids. Now, what is the initial concentration of HS2 minus? Sorry, HS minus, this one over here. Well, it's this concentration, 943, 10 to the negative 5. Now, the initial concentration of hydro of H plus is also 943, 10 to the negative 5. But the concentration of sulfide is just 0. You didn't have anything to begin with. It's an acid base, it's an acid reaction, acid equilibrium, so the change for the acid is minus x, for H plus is plus x, and for sulfide is plus x. So this is going to be 943, 10 to the negative 5 minus x. This is going to be x and x. So Ka2 is going to be, if we go directly to that step, it's going to be x squared. Sorry, not x squared. This is incorrect because the equilibrium concentration of H plus is 943, 10 to the negative 5 plus x. Okay? So here, Ka2 is going to be now 943, 10 to the negative 5 plus x times x divided by 943, 10 to the negative 5 minus x. And for hydrosulfuric, for HS minus, this is equal to 10 to the negative 19. So 10 to the negative 19, if we compare the initial concentration of your acid in this case, so we're looking at 943, 10 to the negative 5, compared to 10 to the negative 19, well, this constant is really, really small. So we can assume that the value of x in the second step is also very small, okay? And, well, our step simplifies to Ka2 equals to x. Well, no, let's do the full thing, right? So it's 943, 10 to the negative 5 times x divided by 943, 10 to the negative 5. And this is equal to 10 to the negative 19. So at this point, then we can cancel 943, 10 to the negative 5 with 943, 10 to the negative 5. And we conclude that x on the second step is equal to 10 to the negative 19. Okay? So this is... Now, one thing that you have to realize here, if you are calculating the concentration of H3O plus, then what you're doing is 943, 10 to the negative 5 plus 10 to the negative 19. Well, actually, this is 1 10 to the negative 19. So this is very small, right? So this is pretty much 943 10 to the negative 5. Okay, so the concentration of hydrogen for H plus, H3O plus, pretty much is just the contribution of the first step. But the concentration of sulfide is going to be 1.010 to the negative 19. Okay, so this is one of the answers that we are looking for. But now the other answer, okay, remember we are asking for the pH of the solution, all right? So the pH of the solution is going to be minus log of 943 10 to the negative 5, and that it's going to be 4.03. Okay, so things to be careful with here. You have to do 2 ice tables or 3 ice tables, all right? But those equilibrium values that you find here on the first step, you are going to use them in the next ice table. Okay, so that's the main thing, the most important thing that you have to remember when working with polyprotic acids. So whatever you obtain from a previous step, you are going to use that as an initial concentration on the second step or the third step or whatever step you're working with. Okay, so as a review here, summary, the polyprotic acid will ionize in steps. So it doesn't matter how many protons you have that you can release into the solution, but you will do that in a step by step. Okay, you release the first one, then you release the second one, you release the third one. And for each one of those protons, you can write an acid equilibrium. Okay? Things to notice here is that successive ionization constants are smaller than the preceding one. So the step 1 will have whatever value it is. The second step will have a smaller value. The third step an even smaller value. Okay? So usually with probably the section of sulfuric acid, because the second step for sulfuric acid is it's rather large constant, there is no significant contribution from subsequent steps to the concentration of H3O plus, okay? But those steps are the only source for the conjugate bases. So for example, in the previous case, if you wanted to know what the concentration of sulfide was, right? Well, that is coming only from the second step. So if you are being asked that, then you have to go through all the steps. If you are just calculating pH, you are perfectly fine just using the first step to calculate the pH, okay? Which is basically what you have here, okay? If no matter if it's diprotic, triprotic, or whatever, if the first ionization constant is much larger than the subsequent constants, then you can assume that the contribution of protons to the solution comes only from the first step. Okay, and then you just use the first step to calculate pH. Okay.